Okay, so we're going to now talk about the classifications of different types of compounds, different types of bonds in particular. Okay, so these are binary compounds, two atoms together, making one bond. What are the different types of compounds you can make? We classify them in three groups: ionic compounds, where there's electron transfer, covalent compounds, where there's electron sharing, and metallic bonds, okay, metallic compounds. When we'll talk about the differences between all those in this video. All this is based on electronegativity and the differences in electronegativity between two atoms that are being bonded. And so that's the starting point. And so you can actually YouTube, there's this really funny and very cute video with these dogs bonding and making bonds where they're playing tug of war. It's got like 1 million views or something like that. But it's pretty cute how this lady trained these dogs to explain this concept of bond polarity, right? That's how unequally electrons are shared in a bond, and it's very simply calculated using just calculating the difference in electronegativity, delta En. So there's two types of covalent bonds, and this is really a continuum: polar versus non-polar covalent bonds. In a non-polar covalent bond, you have a symmetric distribution of electrons. Strictly speaking, this really only occurs when you have the same two elements bonding, or two elements with exact same electronegativity, right? Once you have two different elements with different electronegativities, for example, in hydrogen chloride molecule, you have an asymmetric distribution of electron density, because chlorine is far more electronegative than hydrogen. If you go back to our chart here, chlorine is what, 3.0, and hydrogen is 2.1, so you have a delta electronegativity of 0.9. Chlorine is going to pull more of the electron density towards itself. So really in that bond, the bond is made up of two electrons, but more of those two electrons are towards the chlorine side of the molecule versus the hydrogen side of the molecule. And there's different ways that people try to show this pictorially through some like electron distribution map. So yeah, so if you look at like hydrogen fluoride, that's another similar type of example. Again, fluorine is more electronegative than hydrogen, so you're going even more so here. You have a delta electronegativity of 1.9, and so you're going to have more electron density going towards the fluorine. The fluorine is going to be partially negative charge. We use this lowercase delta symbol to indicate partial charges. So we can put a delta minus charge on the fluorine and a delta positive charge on the hydrogen. We can even draw a dipole moment arrow showing that the dipole moment, there's a dipole established here going towards fluorine. The convention is to draw the arrow towards the negative charge. That's here shown again, just with different colors. So again, getting to the types of bonds, this is really the important part. Ionic. Ionic, you normally have a metal and a non-metal. Why? Well, in those cases, you have really strong, a really high difference in electronegativity. There's different thresholds that people use to say, where is it ionic and where is it covalent? But if you have a metal and non-metal, let's say you have calcium and, I don't know, sulfur, calcium and chlorine, right? You have, in that case, you have a difference of 2, okay? And so metals and non-metals tend to give you ionic compounds because you have such an unequal sharing. You have such a strong dipole that you actually have electron transfer effectively, okay? Where do you call that? Electron transfer, ionic versus covalent, that's, again, arbitrary a little bit. But that's the trend. As greater difference in electronegativity with metals and non-metals that occurs, you're gonna have ionic, okay? So that's metal and non-metal typically. Covalent, sharing of electrons. Typically, that's going to be non-metal, like hydrogen chloride. Hydrogen and chlorine are both non-metals. Non-polar covalent, equal sharing, we went over that. Polar covalent, unequal sharing. And a metallic is going to be metal plus metal. Sorry, that's cut off. Delocalized. In this case, you have a delocalized sea of electrons. The electrons, it turns out, in this case, aren't really associated with any one atom, the valence electrons in that bond. They're kind of moving back and forth. They're very fluxional. This is what gives rise to metals' ability to conduct electricity. It's because the electrons can move around in the so-called sea of electrons, this delocalized sea of electrons. And we know that the flow of charge is what electricity is. So this is why metals are good conductors. Here are some examples. Ionic compounds of metals and nonmetals, so like sodium chloride and zinc oxide. Nonpolar covalents are going to be ones that have the same atoms in them, so like diatomic chlorine or diatomic nitrogen. Polar covalents, ones with nonmetals and nonmetals with different atoms, so they have different electronegativity, like fluorine is more electronegative to phosphorus, so phosphorus trichloride is going to be a polar covalent. Hydrogen chloride, chlorine is more electronegative than hydrogen. And then metallic bonds, sodium and sodium, or it could be, you know, two different metals. It doesn't have to be the same metal. Copper and zinc, that would be an alloy. Copper and zinc alloy is brass. So how do you actually all put this together? It's through a really nice schematic, which is this triangle right here. And what this triangle shows you is basically these four different types of compounds, well, three or four, depending if you break up polar covalent and non-polar covalent in your head, where they are in this space. And the space is the delta electronegativity, and that's what we've talked about so far, but also the average electronegativity, okay, of the two elements. So if you have something like copper and zinc, okay, this is a metallic bond. If we go back to copper and zinc electronegativities, the delta electronegativity there is 0.3 only, okay? The average electronegativity of copper and zinc is going to be 1.9 plus 1.6, which is what? 1.75. So your average electronegativity there is going to be over here, 1.75. But your delta is only 0.3. So you're going to be a metallic bond. Basically, what this portion of the triangle is trying to tell you is that if you have very similar electronegativities and you're low electronegativity, that's metallic. Because if you're low electronegativity, you have metals. And if you have similar electronegativities, well, then it's a metal plus metal. So that's a metallic bond, right? If you have a big enough difference in electronegativity, then it doesn't matter. In order to have a big difference in electronegativity, you need to have a non-metal or metal. So that's going to be ionic, right? But if you have a non-metal and a non-metal, then you're going to be a covalent, okay? And you're going to be a high average electronegativity because you have non-metals, which are on the right side of the periodic table, and both of those, non-metal plus non-metal, both of those elements are going to have be very electronegative. So your average electronegativity is going to be very high. And if you have, you know, sort of the intermediate between ionic and covalent is polar covalent. We said that once you get polar enough, it turns into ionic and probably is going to have a metal then involved. So this is, you know, it's always nice when you have sort of a unifying theory that brings everything together. And this triangle does that in a very nice pictorial way. What you can do is think about what are the extremes of this triangle. Well, the extremes are going to be with the most electropositive and most electronegative elements. The most electronegative element is fluorine with an electronegativity of 4. The most electropositive element is cesium with an electronegativity of 0.7. It could also be francium. They're about similar, but francium is so radioactive that people don't work with it hardly ever. So for practical purposes, it's cesium. So what does that mean? That means at one extreme vertex of your triangle, you're going to be diatomic fluorine. That is has an average electronegativity of 4, right? Because that's what this absolute thing says. It's the average, right? Just summing them up. So it's going to be 4 plus 4 divided by 2. That's 4, right? Because they both have electronegativities of 4. This cesium has of about, here it's saying 0.75 or 0.7. So fluorine is covalent, and it's non-polar covalent on the bottom right of this, right? Because it's the same element. Then you have all these different other elements marching across the bottom here until you get to cesium. Cesium is going to be, cesium-cesium bond is going to be a metallic bond. Its average electronegativity is very low. That's going to be the other vertex of this triangle. It makes sense because cesium is a metal. And then at the top of the triangle is going to be cesium fluoride, right? Because this is the really electropositive matched with the really electronegative. That's the biggest difference you can get, a little bit more than 3. And it's at the center because it's halfway between cesium and fluorine. And then on the edge, you're going to have all your cesium compounds, different cesium compounds. And on the right, you're going to have all your fluorine compounds. And then in the middle, you're going to have all these different things. So you're going to have some polar covalents, like over in this area. So examples would be BBr3, water, Probably boron trioxide falls in this category. Yeah, I believe it does. Carbon dioxide, and then as you get lower here, some people might call these more nonpolar nitrogen monoxide or carbon tetrabromide. But again, the distinction there is kind of a gray area, not too important. You could have certain alloys here, like a strontium magnesium alloy that's shown, that would definitely be a little bit polar, but certainly metallic in nature. And then ionic compounds up here towards the top, like beryllium oxide, lithium bromide, lithium oxide. So this is a really nice way of, I think, visualizing the bonding space in binary